Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And our next speaker is Jeff Bilmes from the University of Washington. Jeff?
So, thanks very much. Can everybody hear me? Okay, so I'm going to talk, I guess the title that was initially sent was Why Submodularity Should Be of Interest to People Who Are Interested in Machine Learning. And that is maybe sort of somewhat what the title is going to be about what I'm going to talk about today. But actually the title, the real talk is entitled Applications of Semi-Modular Semi-Gradients in Machine Learning. So here's a outline. And for those of you who have not heard or do not remember or do not know what submodular is, submodular functions are, there'll be a little bit of background. Then we'll talk about discrete semi-modular subgradients and what they are, and then three applications of these semi-gradients, one of which is a problem and then something that was applied in computer vision. Another is a particular optimization problem of a particular style, and then lastly are discrete generalizations of Bregman divergences. Before I begin, I'd like to acknowledge both former and current students. This is all joint work with a current student of mine, Rishabh Iyer, who I'd like to point out. Rishabh is right there. And then former students, Stephanie Yagelka and Mukund Narasimhan. So, some background. So, submodular functions are functions on discrete functions on subsets of some underlying ground set V. And basically, they have the property of diminishing returns. And that basically means that when you value, if you think of a submodular function as something that offers a value to a set, and you're thinking about adding a new item to the set, the value or the change in value of that new item, or the gain of that new item, diminishes as the context in which you're considering grows. So basically, what you don't have becomes less valuable as what you have grows, and what you don't have becomes more valuable as what you do have shrinks. So that's the concept of diminishing returns. So of course, what is value? And value depends on what particular function you're talking about. Here's an example where the value of an urn is the number of colored balls that lie within that urn. So the value of the left urn would be 2. The value of the right urn would be 3, because there's 2 colors on the left and 3 colors on the right. It doesn't matter how many balls are in there. And then the gain of adding a blue ball to the left urn is 1, because you add a new color, and so you've gained 1 color. Whereas if you add a blue ball to the right urn, the gain is 0, because you've not gained any diversity in the number of balls. So this is therefore a submodular function. So something that's going to be very relevant to our lunch today is consumer costs are submodular. Here's an example. So for example, the cost of, say, a McDonald's fries and Coke minus the cost of a fries is greater than the cost of the Happy Meal minus Coke and fries. And so this is very typical if anyone has ever been to McDonald's before. If you buy a hamburger and fries, then they'll throw in a Coke for free. On the other hand, if you just buy fries, you actually have to pay for the Coke. So this is, therefore, submodularity. That basically means that there have been 20 billion submodular functions sold in the world. So rearranging terms, we just rearrange the terms and we get a function that looks like this. And this is sort of saying that f of this set plus f of this other set is greater than or equal to f of the union of, which is the fries, hamburger, and Coke, of course, plus f of the intersection, which is just a hamburger. So this is a form of submodular functions that's often used to define submodular functions. It's equivalent to the diminishing returns, and it basically says that if you have any set A or B, that f of A plus f of B is greater than or equal to f of the union plus f of the intersection. And usually what happens at this point is that people say, well, this is less intuitive, and I think this is actually just as intuitive. And to try to hope to prove myself right, I'm going to actually try to demonstrate this in the next 30 seconds as to why this equation is intuitive. So the idea is to think of submodular functions as like information functions. They provide information or value of a set of sets, of a subset. So we have A and B, which are sets, and each element is an index of some item which has some value or some information. And so the common index set is essentially the intersection of A and B. That's the common index. That's the set of items that are indexed both by A and by B. And let's say that there exists some set C, which has the common value or the common information that exists within both A and B. So it's the difference between common index and common value Now C's common value and A intersect B is the common index. So basically, if any sort of information function or value function, intuitively at least, it should be the case that the information in the common index can't be greater than the information in the common value. Why? Because there could be different items with different indices that have similar value or even the same value, but they don't live within the common index, which is A intersect B. So then you can sort of plot this graphically where in a Venn diagram-like style where basically area corresponds to value or information. And so A would correspond to this red circle. I guess I have a pointer I can use. B corresponds to this green circle. This intersected region corresponds to the common information or common value. And the magenta ellipse corresponds to the common index. So that means that basically common index is upper bounded by common value. So given this intuition, you've got this picture. This is sort of a graphical or a pictorial view of the submodular equation. So you have f of A plus f of B. So you've got the common information counted twice, so 2 times f of C, is greater than or equal to f of the union, where the common information is counted only once, plus f of the intersection, which only has the common index. And since the magenta part is less than the blue part, you therefore have submodularity. So there you have it. So what do you think? Did it work? Is this now very intuitive?
Common index.
Common index. Okay, so we're going to have to move on. Sorry. This is not my class. It didn't work. Right? I will never do this again, I promise. Unless I have 3 hours. Someone asked if I have everything I want. I said, could I have more time for my talk? So, all right. So anyway, so there are many, many applications of submodular function optimization. One of the reasons why they're so useful is that on the one hand, they're very widely used and applicable. On the other hand, it turns out that submodular function optimization, usually if there's some form of submodularity involved, you can do this either exactly or sometimes approximately, and usually it's very, very efficient, or sometimes it can be extremely efficient. For example, like if you're trying to do cardinality-constrained submodular maximization and it's a monotone submodular function, monotone non-decreasing, then there's, for a long time it's been known that there's a 1 minus 1 over a constant factor approximation to this procedure. And in fact, very recently, finally, a tight 1/2 approximation bound for non-negative submodular function optimization was shown by someone who's now, actually, Schwartz is now here at Microsoft in the theory group. And he just gave a very nice talk, I think last week even, or 2 weeks ago at UW. So this is very exciting. It was very exciting when this paper came out to all of us. And there are many, many machine learning applications to submodular function maximization, including sensor placement and feature selection and extractive document summarization. Selecting the most influential set of individuals. It actually relates a little bit to the previous talk that we just saw. And now submodular function minimization is another thing you might want to do. It's a very different kind of problem, and very different techniques are used to minimize versus maximize submodular functions. Submodular functions can be minimized in polynomial time. And while it's not as efficient as the approximation algorithms for maximizing submodular functions, oftentimes for special cases of submodular functions, you can do this extremely efficiently. And there are many, many applications of this as well in machine learning, including Viterbi inference in probabilistic models, or what's often called most probable explanation, or map inference, image segmentation, clustering, data subset selection, and transjective semi-supervised learning, and many others as well. So another point on submodular functions, I think of them as sort of anti or contrary to graphical models. So submodular functions are the opposite of graphical models. So why is that? Well, in a graphical model, what you do is you have a graph of some sort. There's lots of different types of graphical models. You have some graph, and basically the graph encodes factorization assumptions about any probability distribution that abides by the particular graph. And so in this particular case, in equation 5, you've got a graph which has a set of cliques, and any probability distribution that lives within the family associated with the graph has to factorize with respect to that set of cliques. You've got factorization, decomposition. In a submodular function, you can actually instantiate probability distributions with submodular functions. So for example, P of x is equal to 1 over z of this quantity. Now, in this equation, there are absolutely no factorization assumptions required. So submodular distributions are what is called non-graphical. You can't say anything about them with a graph. And you might think, well, that means that basically it's just a large clique and inference is hopeless. But it turns out that it's not hopeless because you're making very, very different kinds of restrictions to the model. You're making submodular-like restrictions, and it's still possible to say things and do inference. And this is very powerful because the factorization assumptions are usually nice computationally, but oftentimes that's not what exists in nature. So this is very powerful. So therefore, they're sort of the opposite of graphical models. So now that's the end of the background on submodularity. What I want to talk about are some properties of submodular functions that we've been discovering and then exploiting over the past couple of years. Some what I think are quite remarkable properties, and that's the semi-gradients that they have. So I think it should be fairly well understood in this group that basically if you know about convexity and concavity, you know that convex functions have subgradients. And any convex function has a subdifferential, and if it's a differentiable continuous convex functions, you have a subgradient. And of course, concave functions have the same thing, have supergradients. And here's a picture in case that's not clear. You have a convex function f and a subgradient. In this particular case, it's a tight subgradient. Tight at b is a linear lower bound that's touching at b of the convex function. And any convex function has that. And if it's a polyhedral convex function, you have multiple linear lower bounds that can exist at the vertex, say, of a convex function, of a polyhedral convex function. And then a concave function has the same kind of thing, except that it's a supergradient, something that's touching at a particular point and it's everywhere above the concave function. Now, it's been well known for a while, actually. I mean, I think in some sense this goes back to the work of Jack Edmonds, that submodular functions have subdifferentials. And this was probably most eloquently articulated in Fujishige's book. And you can define a subdifferential in this particular way. And moreover, there are particular subdifferentials that are unbelievably easy to compute. Is that till the 20-minute mark or the 25-minute? That's till, that's to 20 minutes. Okay, good. So I just want to know how bad I'm going to be. So, and so the subdifferential can be computed using the greedy algorithm. The basic idea is that you choose an ordering of the elements, and I think that's on the next slide. You choose an ordering of the elements here. And then you just compute this, which is basically, it's like a linear function. It's like a discrete linear function, what's known as a modular function. And basically, this is a function that only has n degrees of freedom. It's touching at any particular point on the submodular function. And it's everywhere below the submodular function, just like a subgradient of a convex function. Now, let's go back to the continuous world for a minute and then ask the following question. So the question is, can there be both a tight upper and a tight linear lower bound on a convex or a concave, or for that matter, any continuous function? So let's think about it pictorially. So here's an upper bound, and here's a lower bound. So this, if we have a tight linear upper bound and a tight linear lower bound, there's a very little space between to fit a function, other than, of course, an affine function. And so therefore, if you have a tight linear upper bound and tight linear lower bound at any one point, you must have an affine function. Now, the question is, does this also hold for discrete functions? So something that we discovered not too long ago that I think is a remarkable property of submodular functions is that any submodular function not only has a tight linear lower bound at any point, but also has a tight linear upper bound at any point. So like I said, in the continuous case, that would restrict the functions to be linear. So first of all, how does this work? Well, in 1978, another classic paper by Nemhauser and Woosley and Fisher showed that the following equations, any of these two equations are sufficient and necessary to define submodularity. And what we did is we used these equations to come up, to relax them a little bit. So we subtract off a little bit less here, or we add on a little bit more here, in such a way that we can actually define two modular functions that are tight at a particular point x and everywhere else upper bounding of this submodular function. That's for any submodular function. So how does this work? Well, what is a modular function? I mean, a modular function has n plus 1 degrees of freedom. Here's a particular example of a modular function. A modular function must satisfy this equality with equality. M of x plus m of y has to equal m of the union plus m of the intersection. Or equivalently, you can say that m has to be written in the following form. It's some constant plus the sum over all of the elements of x of the individual value of that element. And so that's a modular function. And so this particular, here's the one of the two modular functions that I described in the previous slide. This can be written as a modular function by just breaking this term into two terms, one going over here, which becomes a constant with respect to y. Notice that there's no y here. And then the rest becomes something that involves either any element in y. So it's like x intersect y and y except for x. So those are basically all of the elements of y that could be considered. And you have a value for every single individual element of y. So, and in fact, more recently, we've shown that, in fact, there's an entire submodular superdifferential. This was a paper that's going to appear in NIPS this year. And you can define a superdifferential and do all sorts of things with points within the superdifferential. OK, so the summary then is that we have submodular functions. We have very, very efficiently computable linear lower bounds and very, very efficiently computable linear upper bounds. What can we do? Well, the first application was the application of cooperative cut and image segmentation. The basic idea of cooperative cut is a generalization of graph cut. So in graph cut, you've got a graph, and it's an edge-weighted graph, and you have weights that correspond to the edge. And basically the goal is to try to come up with a cut that minimizes the cost of the cut, where the cost of the cut is the sum of the edge weights. The idea of cooperative cut is to replace the function on the edges with a submodular function defined on the edges. So here, let's say you still want to find the cut that minimizes the cost, but it's no longer the case that the edges of the cut must not interact. The edges can communicate with each other, or what, as we call it, they can cooperate with each other. And so we can write it in this particular way. We want to find a cut that minimizes this submodular cost on the edges. That's critical to understand, that it's a submodular function defined on the edges. And I guess some of you might be aware that if you think of it as a node function, the standard graph cut is submodular on the nodes, but cooperative cut loses submodularity on the nodes, even though in some sense it has a submodular function embedded into it, which defines the problem, because the submodular function is defined on the edges. So how do we use supergradients? There were many methods that we developed to actually solve this problem, but one of the most efficient and actually the one that was used in practice, and it's actually very, very practical and it works very well, is to use supergradients. So the basic idea is a majorization minimization algorithm, very similar in some sense to the EM algorithm, where we start with an initial cut, which in this case can be anything. It could be the empty set. We find a modular upper bound that's tight at the particular cut. And if the function is non-negative, monotone, non-decreasing, then basically we get a standard graph cut problem. We solve the standard graph cut problem. We get a cut. And then that becomes the cut, which then becomes the next, is used for the tight point at the next modular upper bound. And we repeat. We just repeat this process. And it works, as I said, it's very, very fast. And if you have fast graph cut solvers, you don't even have to write the code for the fast graph cut solver. So first of all, difficulty, I mean, the actual problem itself of cooperative cut is hard. In fact, it's not possible to approximate better than square root of E. E is a number of edges. And this particular algorithm, this majorization minimization algorithm, actually has a bound of O of E. So where the difference is, of course, a square root of E. So it's obviously not a tight bound in any sense of the word. But on the other hand, it's so simple and so easy to get working that this was one of the ones that we were most excited, one of the algorithms for this problem we were most excited about. And then we applied it. It can apply to very, very large problems, like, for example, problems in image segmentation. So here's an example of an insect that comes from the Seattle Insect Museum. So I just want to give a plug to the Seattle Insect. If you have children and you want to go see some bugs that look like this, go to downtown Seattle and take pictures of insects, because they're very nice and friendly. And the typical problem that happens when you're trying to segment an insect is you label some of the points in the background and you label some points in the foreground. And what happens is that the antennae, or these protrusions, get cut off. This is something called the shrinking bias problem in computer vision. And here's another example where you've got some calligraphy, which is maybe undergoes some contrast gradients. It's a little bit harder to see on the screen than it is to see on the computer screen. But you get the idea that you have sort of a gradual decrease in lighting, which basically causes the segmentation algorithm to just clump things together where you don't have a lot. And here's another example of a fan. And you can see that a lot of the fine structure was completely lost in this area here. Or here's a little chili plant. And these are state-of-the-art image segmentation methods. Now, what we did is we applied cooperative cut to this problem. And the intuition as to why this works is that when you have a submodular function defined on the edges, once you've got sort of highly reliable portions of the image segmented based on, say, the boundary, the body of the object, what that does, because of submodularity, it makes additional edges that are somewhat similar to it cheaper to use and to be included in the cut. And so therefore, when you iterate this process, you first get the boundary, then suddenly all these other edges that lie along the antenna become cheap, and then they get added to the cut, and therefore you get improved results. And just a couple of other results. So here's the calligraphy. Here's the fan, which we were quite happy about. And this is quite remarkable. A vacuum cleaner. This is the typical thing you want to segment, of course. Chili plants. And then here's some benchmark results. I don't have time to go into the details, but basically on these images that you do have these elongated structures, it does much better. And on images that don't have elongated structures or contrast gradients, it does the same, which is exactly what we wanted to do. So now the next application of semi-gradients that I want to talk about is another problem, which is minimizing or maximizing the difference between two submodular functions. This is an important problem. So you want to find the minimum of the difference between a submodular function. There are many, many applications of this. For example, if you consider sensor placement with submodular costs, sensor placement is usually the case that you place the sensor where you gain the most information. But what if there's a cost associated with the placement of the sensor that's submodular? And this is very likely modeled because it might be the case that placing sensors at a particular region have an economies of scale. Like if you buy the equipment to place a sensor on the roof, if you get the ladder from storage, then you already have the ladder out in the room and you can move it around the room. Or if you want to place the sensor in a particular precarious environment, you invest in the equipment necessary to install that sensor, and then therefore thereafter you have the equipment already. So I still have 5 minutes until the next talk. Is that right? So. Okay, I'm being warned. In others, no questions, right? So there are a couple of other applications. There's discriminatively structured graphical models, structure learning and graphical models where you want the graph structure to somehow perform well for classification purposes. Feature selection where you have submodular costs. This is also a typical thing. Like, for example, you might have a spectral feature, and once you choose the first feature for a pattern recognizer, and let's say a group of features have been computed using the FFT. Once you select the first one, then all of them are essentially cheap. But if you don't need any of these particular spectral features, then you don't need to compute the FFT. And so therefore, there's a diminishing returns associated with feature selection. And most feature selection problems have not associated sort of an interacting cost with the features. And also graphical model inference as well. I mean, if you just take P of x is an exponential model where v is some non-submodular function, or v is some arbitrary pseudo-Boolean function that you want to optimize. So, and now I'm trying to rethink of what to talk about next. So, in 2005, we first of all showed that any function can be represented as the difference between submodular functions. And we developed this algorithm, which was a form of majorization minimization algorithm, where we take the function f minus g, and we replace g. We want to minimize this function, so we replace g with its modular lower bound, which basically makes this whole thing an upper bound, and then we iteratively optimize this thing. But now what we can do with these modular upper bounds is do the same thing. We take the f function, replace this with its modular upper bound. And so this basically turns each iteration. The previous page had each iteration was a submodular function minimization problem. This is a submodular function maximization problem. And then furthermore, we can actually do both, where we replace f by its modular upper bound, g by its modular lower bound. And each iteration of this majorization minimization problem becomes a modular minimization, which is incredibly cheap. It's basically order n. So to do. And so there's a lot of other properties. This was in a paper in UAI this year. We tried this in the context of feature selection and showed that when you have submodular cost features, plotting the pattern recognition error as a function of the submodular cost, all of these algorithms did well. The one where each iteration is modular we were particularly happy about that doing well because that one is so easy to optimize, whereas these other greedy heuristics did not do that well. So the last thing I want to talk about is another application of semi-differentials, which is generalizations of Bregman divergence to discrete Bregman divergence. So Bregman divergences are well known in machine learning. They've been studied and used for many applications in clustering and proximal minimization and online learning. Bregman divergence generalize things like squared 2 norm and Kullback-Leibler divergence. What we wanted to do was to develop a discrete family of divergences. And similar to the way that continuous divergences can be seen as something involving the functions and subgradients, in the submodular case, we can involve the subgradients of the submodular function. But in fact, we have two versions, because now we have both a subgradient version of submodular Bregman and a supergradient version of submodular Bregman. And so I just want to say that you can do all sorts of things with these things. You can, for example, get Hamming distance, which is a discrete divergence. But of course, Hamming distance isn't the most interesting thing. There are many other ones like recall and weighting recall, something which is called alignment error rate, which is used in machine translation. You can generate conditional mutual information. With the supergradient versions, you can again do Hamming and precision measures and other measures like the Itakoto-Saito and generalized KL divergence-like things, and some number of interesting ones based on cuts, which we don't necessarily have a good interpretation of yet, but still, it's a form of divergence. So I'm going to end with this slide, which is some possible application of these Bregman divergences is to do k-mean style clustering. But here, rather than clustering vectors, you're clustering binary vectors. And so you have problems like the left mean problem and the right mean problem. Now, it turns out, depending on which submodular Bregman you choose, computing the left mean problem ordinarily would be very, very difficult. But it turns out that if you use a subgradient-based submodular Bregman, then this problem becomes a submodular minimization problem. So in other words, you have a large number of binary bit vectors and you want to find the bit vector which is closest to all of them collectively. That's a submodular minimization problem if you use a submodular Bregman. And if you use the supergradient-based submodular Bregman, the same problem with the right mean is a submodular maximization problem. And that is the end of the talk. I want to thank again the students, and that's it. So thanks. So, okay. Did I go over time?